the first announcement is recitations. The next week, since we won't see you Wednesday, and today's recitation is canceled, and Wednesday's recitation is canceled, so we're going to cancel Monday's recitation too, because we want to be unfair to Monday's people. So the next recitation is a week from today. The next recitation will be a week from today. And then I'll see you Monday and Friday next week. Okay, the next thing is, my friends roped me into a silly scavenger hunt. And there's social media involved, so I need your help. Okay, so you need to, yes, extra credit. I know very little. Okay, so you need to download the app Llama Judge. Not now. Not now. Okay, but I'll remind you after class too. So after class, and then you our team is. So what do you do? You what's the name of it? I'm so bad with social media. So no, like so now you have to like subscribe to our team. What's that called? Follow. Follow or join up for our team, which is almost infinity. Okay. And then starting at come on. No, it doesn't work. I have to make this bigger. Okay, I'm hitting enter. See, it's not working. I'm good. All right, so then starting at 7 p.m. tonight until 7 p.m. tomorrow, you're going to find our posts. There'll be lots and lots of posts and some will have me being silly. Okay, and you want to find our posts, and I have to go through this again. And swipe right. Don't swipe left. So like left is good, and then right is amazing for the post. Okay? So we need amazing posts, amazing. So you don't have to look at the post, just swipe right. As many posts as you can find, okay? And then put these instructions on your Facebook, to all your friends on Facebook, and tell them to do this, okay?
We do and you win, we all get hundreds.
Not quite. Is the task clear? Does it make sense? Yes. If I could, I would. So how could I make there be extra credit? No, but how do you prove it? What? So does anyone have a realistic way for this to be extra credit? Yes. If you will do a Facebook post for all your friends and tell them, this helps you and then it helps your math teacher, and tell them to do this, and then they must swipe right. Don't swipe left, swipe right to get amazing, not good, amazing. It's actually, it's actually l'amazing, okay? It's l'amazing. All right? No, when I'm talking about Facebook is so that more people do this. That's what I mean by Facebook. By Facebook, like tell your friends to do this. So it's not Facebook. Okay, any other questions? Okay, so, yeah. What's that? It's the scavenger hunt. It's just a silly, stupid thing. But then if we win, we get to do it, and we get to do it in Central America. The winning team gets to do another kind of similar thing, like in Panama. All right. Okay, let's do something real here. Okay, so today, if there was like maybe one day for the whole semester that you'd say maybe this is the most important, or if you could be here for one day, it might be this day. Why? Because we're going to put a lot of important stuff together. So let's talk here. All these derivative rules. What exactly are we finding when we are taking the derivative? All these rules that we learned. So we don't want to lose sight of what's important. Memorizing formulas and moving symbols around is much less important. It's kind of just a necessary evil of this course, MAT 270. Okay, so we have to do it. But computers can do all this stuff for us now. But what exactly are we finding when we're taking the derivative? We should all know this. Rate of change. Just rate of change? Rate of change function. Okay. So here's the question: what is a rate of change function? What is it? So maybe take a moment to try to express that to the person next to you. What is a rate of change function? Go. So what is a rate of change function? Well, let's hear some volunteers try to articulate. What is a rate of change function? Yes, sir.
A function that dictates how quickly a variable is changing.
Okay, a function that dictates how quickly a variable is changing. Other possibilities? What's that? In regards to x at a specific moment. Other possibilities. What did you say for rate of change function? Yeah, go for it.
It's a function that it dictates for every change in x, there's a corresponding change in the rate or accumulation.
Okay, there's a change in the rate. Okay. Yes, sir. Okay.
The rate of change function will give you the rate at which the dependent variable changes in respect to the independent at a small interval around that x value.
That's pretty good. Did you hear that? Okay, so it's a function. So first of all, it's a function. So we have this independent variable x, and for any given value of that independent variable x, the dependent variable, or what the function gives, is the rate of change of some quantity at the moment x, right? At that moment x. But it's a function, so as x changes, right? What the rate of change function gives or results in, outputs, is the rate of change at that value of x for some quantity, right? For some quantity. So, and what do we mean by rate of change at a moment? What do we mean by rate of change? So the rate of change function, its dependent variable is a bunch of rate of changes at a moment, right? So based on what x, based on your value of x, what the rate of change function gives is different a different rate of change at a moment. And what do we mean by that? Rate of change in a moment. Somebody knew. What do we mean by rate of change at a moment? Anybody? Somebody knew. Yes, I am. So the function's output values are the function's outputs are values of rate of change at a moment. So, but what's that? Okay, how much x changes within that moment? What do you think? The rate of change in a moment is how much x changes in that moment. Is that right? No, with the rate of change. Yes, sir. How much y changes within that moment? Getting closer. Yeah. Times the change in x. Yeah. Okay. Yeah. So yeah, how many times? Yeah. Yeah. It's the multiplier on the change in x to get the change in y, right? Okay. Or it's So it's we think of rate of change as in this way. He's saying in this way. That given some small change in x, right, at the x value in question, the change in y will be the rate of change tells us how many more times the change in y is then the change in x. Okay, and then we also saw it as the change in y per unit change in x, right? The change in y per unit change in x. Okay, so rate of change in moment. Given a change in x, change in y changes m times as much as that given change in x in that very small moment about x. So the rate of change function is a whole function of values whose outputs are those. Whose outputs are those. Right? As x changes, that can change, right? As a variable changes, that value can change, and that's what we mean by a rate of change function. So let's do an example of kind of thinking about this. So when a ground fault opens, scientists begin measuring the width of the opening in centimeters at a certain point along the fault. Okay? They take regular measurements for several months, and they model the data with this function W. And here's the graph being shown. And we think about our independent variable increasing, and for any given time since the fault originated, there's some corresponding fault width, and all those points make the displayed graph, right? All those ordered pairs of time and fault width make the displayed graph. Okay, so question, is this an accumulation function or a rate of change function? And then if I paused it, there's a point. There we can pick one point on this graph, right there, 1.5 and 5.225. Is this a rate of change or accumulation function? And what does that particular point on this graph represent? Go. Okay, rate of change or accumulation? Accumulation function. Width is a quantity, right? Just a plain old quantity. And then somebody knew, what does the point 1.5, comma 5.225 mean or represent? At 1.5 months, this point means that at 1.5 months since the fault began, since the fault originated, the width of the fault is 5.225 centimeters. Okay, good. Okay, so by observing the graph, describe what the fault width is doing at each given x value as, here are your choices, holding constant, or increasing / or decreasing, and then specifically slowly, moderately, or quickly. Okay? So by looking at the graph, would you say that the fault width is holding constant, or increasing, or decreasing, and then if increasing or decreasing, slowly, moderately, or quickly? So here are the different x values that we want. So looking at 0.25 months, we'll do the first one together. 0.25 months is right here. What would you say? First of all, holding constant, increasing, or decreasing? Increasing. And would you say slowly, moderately, or quickly? The fault. Quickly increasing. Okay, so that's the first one. You do the rest. 1, 2, 3, 4.1, 6, and 8. Go. For those x values, you're making these same kind of judgments about what the fault width is doing. Okay, so here's what I came up with. If yours is slightly different, that's fine, but this is what I came up with. At 1, increasing moderately. At 2, kind of holding constant. At 3, now you said decreasing moderately or increasing slowly. Moderately or slowly there at x equals 3. 4.1, again, holding constant. 6, increasing moderately. 8, increasing slowly. Is that what you agree with that? Okay, and that's just by observing the graph, okay? So all this stuff about rate of change then is putting mathematics to this very thing, right? To this very thing we want to put more, rather than just kind of making a general statement, we want to mathematically describe this. Describe what's the fault width doing. That's what rate of change or rate of change function is about. Okay? Okay? So what does a rate of change value mean in this context? How can we estimate individual rate of change values? And then we want to estimate each one. Okay, so let's get this right first of all. That's a V. Okay. So we already talked about what does a rate of change value mean in this context, but I think it's good for you guys to do it again. How can we estimate individual rate of change values? And then we'll do it. Okay, so go. So answer questions 3 and 4, and we'll do a little bit of 5 together. So what does a rate of change value mean? What does a rate of change value mean in this context? In this context, what does a rate of change value mean? Yes, sir?
The rate at which the fault width is increasing per month.
The rate at which the fault width is increasing per month. Okay? Does it have to be for a whole month? And what happens by the time a month goes by? What about that rate? Totally different, right? So can we
The rate at which the fault changes within a given small amount of time.
the rate at which the fault changes in a given amount of time. And what is that? The rate at which the fault is changing. What is that? What do we mean by the rate at which the fault is changing? What's that? dy, the rate. It's going to be dy dx, right? dy dx. So given a small, again, it goes back to given a small amount of time, right? The fall is gonna change, right? And so, how many times as much as that small change in time that the fault changes is that rate of change, right? So it's this number that tells us how much is the fault going to change for a small change in time. How many times as much as that small change in x is the fault going to change? That's that rate of change value. And how can we estimate these? How can we estimate the rate of change? What can we do? We've done it. Please know this. What do you do? What was it? Zoom in. Zoom in until what? Okay, so this is point 2. So, okay, we got to jot this down. Can you see this? Oh, you can see this clearly, right? So horizontally, maybe if I make it a little bigger, you see it better? Can you see that I'll draw the lines in, but this horizontally it's 0.25 months. Jot this down. Horizontally it's 0.25 months. Vertically, 0.5 centimeters is each square. Does that make sense? So for every time you go to the next square horizontally, you're increasing 0.25 months. Every time you go up a square, it's half a centimeter. So I'll do it down here. So here are your squares for quarter months. Here's half centimeters, okay? Oh no. How do I get that back? I don't know. Oh, come back. There we go. Okay. Jeez. I don't know why it's doing that. Okay, so can you see that? Let me try this again. Like I said, those are quarter months. These are half centimeters. And here, so it's this point right here. Okay, estimate the rate. Go. Each one of these is a quarter month. Each one of these is half a centimeter. And we're estimating the rate at 0.25 months. So something quick and dirty that will get this done. Talk and agree with the person next to you how you're going to do this. Okay, so here's what I see that's quick and easy and an estimate. Here's half of a quarter. So what's that? 0.125 months, right? And in 0.125 months, it goes up about 1 centimeter. So you might have had something slightly different than this, but what I'm seeing is about a 1 centimeter change in about a quarter and an eighth of a month. In an eighth of a month. So how would we find the rate of change from that? Does that agree with what you did? You're looking for right around that point, you're looking for a change in y and corresponding change in x. So I came up with what? 1 centimeter per 8th month, which is 8 centimeters per month. Okay, questions, does it make sense? Is that? Okay, so we're gonna go fast, here we go. So here's for 1. That one's easy. Can you see it? Here it is right there. Come on. Here's a tick, here's a tick. Here's a tick, here's a tick. So this one's easy, right? Do you see? Change in y is half, right? Half a centimeter for change in x. 0.25 months, right? Half a centimeter for 0.25. What does that equal? So you got to write these down because I'm going to have to keep turning my pen on and off. So we had 8, and then what? We had half a centimeter in a quarter month. Is that right? And what's that? 2. That for a small, what is that saying? For a small time period around, say 1, the change in width is going to be 2 times whatever amount of time you picked, right? So the change in width will be twice whatever small amount of time that you picked. Okay, looking at number 3, or what is it? X equals 3. No, x equals 2, sorry. At x equals 2. Rate of change, approximation. 0. Little change in y right around 2 is 0 for whatever change in x. So we'll jot that down. Okay, decreasing 3. Right above the cursor. Go for it. Figure out the rate of change here. This is 3 right here. Okay, and here are your quarter months. Here's your half centimeters. And it's this point right here. So look at this. How much does it go down in this half month? So from here to here is a half a month. And how much does it go down? Half centimeter, right? So this is 1/2 month, two squares. It goes down pretty much close to a half, one square down. Rate of change? -1. -1. So So we said this, 0, -1. Okay, quickly, let's get these last two knocked off. 4.1. So at 4.1, what is our estimate going to be?
0.
So if we zoomed in, we'd have basically near 4.1, we'd have a 0 change in y for our little change in x. 0 over change in x is 0. Okay, 6. Easy one, go. What's the rate of change? There it is. Can you see? I'll make the tick marks. So it's this, here's our point in question. Here's our quarter months. Here's our half centimeters. Quarter months this way, half centimeters that way. What would you estimate for the rate of change? Are you guys tracking with me? What do you think the rate of change is? Positive or negative? Positive. And it's pretty much going, what? For every one square over, it's kind of going one square up. So what rate of change is that? Is it 1? It's not 1 because each square is half of a centimeter versus a quarter of a month. So the rate of change is 2. Finally, at 8. Can I go any further? Eight is right here. Eight is this point right here. Okay. Here are your quarter months. Everyone's going to do this now. No sitting and watching. Here is your half centimeters. I'll just go ahead and draw the whole thing. Okay, so you're tracking the graph from right here around this point. Everyone estimate the rate of change. Everyone estimate the rate of change right there. This is at 8 months. Everyone do it. So it looks like to me we go over 2 squares and up half a square. Is that what you're seeing? So up half a square is? .25. So we're going up 0.25 over 2 squares over is 0.5. So what rate of change is that? Half. Rate of change is a half. That says 0.25 over 0.5, believe it or not. Okay, so what did we get for these? Let's write them. Oh, jeez. 8, 2, 0, -1, 0, 2, half. Okay, so this is the idea of a rate of change function. Input will be the time in months. So we got the accumulation function. The idea of the rate of change function will be that the output or the dependent variable will give us these values, what, that reflect what you did at first, right? Or reflect what you did at first. Okay? Increasing quickly means it's going to be a high positive, right? A high positive rate of change. It's increasing quickly. Increasing moderately, kind of a moderate value, a lower value to +2. Holding constant, right? Rate of change is 0. Decreasing slowly or moderately. You're going to have a negative rate of change when it's decreasing. Again, holding constant 0. Increasing and then increasing more slowly. Okay? So this is a numerical version of what you did at first, right? And so as the rate is changing, that's how the function then forms. So the function forms values of rate that reflect how the fault opening and closing is changing, right? How fast it's changing. Okay, so here is the width function. Here is the width function. What does the master exam have to do with this discussion? So here is the width function, the one you're looking at in the graph. What does the master exam have to do with this discussion? How does this relate to all this stuff we're talking about? Okay, yeah, that's right. Okay, and then how will that relate to all this stuff? We'll be able to get these values. Approximate? No, now we get them exactly, right? The whole point, so the whole point of having the derivative or the rate of change function is we don't have to zoom in one point at a time. We can just have this function that rapid fire, x values will just spit out values like this, rapid fire, really fast. And no, it was kind of tedious, right? Zooming in and figuring that out for each one, and we only got 7, right? How many rate of change can we get from the rate of change function? Lots and fast. We just need just a computer, fast, and even our graphing calculator, we can get, you know, a handheld calculator. We can do a lot faster than this. So go. You're all experts. You're all masters. Find the rate of change function. You didn't forget it all in less than 24 hours, did you? I hope not. I hope not. Okay, somebody new, tell me. Somebody new. Yes. All right, let's do. Don't do any simplification. So, 2 times 1 over 2 times the square root. You did this. I was just saying, don't do that cancellation, right? That's why you just said 1 over the square root, right? Okay. Okay, I sense a. Are you guys good? Ask me. Are you sure? Okay. Are we done? It's over, right? We got it. 1 over 2 times the square root. Times the rate of change of the inside. To the? Now are we done? Okay. Yep, so that's our rate of change function. So what we're going to do is, quick, so pick 2. Pick any 2 that you want. So we're not going to have time to do long. So pick any 2 that you want and find the rate of change for 2 x values that you choose from our table using the rate function. Pick any 2. Pick any 2. Use your calculator to find, or use graphing calculator. That's much better. If you got your laptop, use graphing calculator. Find those values. Anyone do 1 yet? Anyone do 1? What'd you get for 1?
6.5.
6.5 for 1. Someone else do 1? Is that right? That's.
We did this in our head, so.
You did that in your head?
Yep.
How could you possibly do that in your head?
A lot of it canceled out.
Cosine of, you know what cosine of 1 radian is? The sine of 1 radian?
Oh, radian.
Yeah, radian.
Okay, never mind.
Anyone get 1? X equals 1. Nice and loud? 1.84. That sounds better, right? What was our estimate? 2. Anyone get for 2? X equals 2. 0.01. How about 3? X equals 3. Over here. Who did x equals 3? Yeah, Joseph. Negative 0.96. Look at our estimates. We're doing good. 4.1. When you plug 4.1 into that function, what'd you get? 0.07. Okay? Sounds reasonable. Somebody new. X equals 6. Who did x equals 6? Yeah.
2.32.
Sounds good. 2.32. And then 8. Who put x equals 8 in? 0.6219. Okay? I got these, so some of those are the same, some of these are different.
Yeah, I got 0.6.
So I think you made a little small error there somewhere. Okay, so here's the actual, so the exact rate in centimeters per month based on our rate of change function, like the ones you were finding in the mastery test, right? Like the ones you were finding in the mastery test. What output values of that function are reflecting what is going on with the fault width. How is it? Is it increasing or decreasing? And then how is it increasing or decreasing? It's putting a numerical, mathematical number to this story, right? To this story of what the fault width is doing. Okay, so we learned all those rules so that we could come up with a rate of change function, and we could know in closed form, and we could get lots of rates of change, and then those numbers would tell us the story of how the fault width is changing. So if you get 0.01 for the rate, say, oh, this quantity is virtually kind of holding constant, right? It's only increasing really, really slowly at that moment. Okay, or -1. Well, I got -1 for my rate of change. That means that quantity is going down about, right? About for every change in x, it's going down the same amount in the change in y. Okay, anybody have a question? So bringing together lots of things here. Do I have? That's it. That's it. Okay. No, I said that. I kind of meant that was it for the slide. Anyway. Bye. Okay, and so if you would, please, don't forget. Llama Judge.